But if we expose it to ionizing radiation from the natural radionuclides in the background or cosmic radiation, we can promote electrons from their bound states attached firmly to particular atoms into a state of conduction. And they can move in the crystalline lattice. And in some of the defects within the crystalline lattice, we can capture these charge carriers, which puts the system in some ways out of charge equilibrium. That leaves vacant states close to the atomic sites, which can move by charge hopping and also trap signals and information within the lattice about the radiation history. I've got a diagram here which tries to show schematically what might happen to a mineral between its innocent creation in a geological system at time of formation, crystallization, and then the end of its time through my laboratory, when we try to estimate the date of something that happens in between. So I hope you don't mind my simplification of geology into some left-hand diagram that acknowledges that the minerals tend to be formed without trapped charge carriers in their defects. They may be subject to many cycles of alteration of their geological history. They may be subject to thermal alterations. They may change their thermal environment. Radiation history, they will be exposed to natural radioactivity throughout their geological history, and potentially to weathering and sedimentation and then reformation of different rocks. And during this complex set of geological histories, the defects within the crystal may change, and also their contents in terms of trapped charge. They can undergo many hypothetical changes. However, if we reach a point when a sediment is transported and exposed to daylight, or where a rock is heated severely through contact baking in a volcanic system or even cooling from a lava, the trapped charge stored in its prior history can be erased. And we can start a new cycle of buildup of trapped charge within an enclosed sedimentary environment, which builds up in response to the natural radioactivity of the sample and its environment to a level here. We will then collect the sample, bring it to the laboratory, and separate the minerals under darkroom conditions without disturbing the trapped charge if possible. And we will then stimulate the signal by heating the sample to release thermoluminescence, or by stimulation with light, by illuminating it with one wavelength while recording the emitted luminescence generally at a shorter wavelength to remove the signal. And what we want to do if we're trying to date the sample is to then evaluate how much radiation would it have been exposed to explain this natural signal. And we do this in the lab by two different methods using calibrated laboratory sources. If we've removed the signal, we can regenerate a new signal by re-irradiation, and we can measure a regenerated dose-response curve, which we interpolate through to estimate the dose that the sample had been exposed to. That's one way. And the other way is that we can take different portions of the samples, expose them in the laboratory to known amounts of radiation, and construct a dose-response curve, which is an additive dose-response curve, which we extrapolate to estimate the stored dose. So those are two ways of quantifying the signal and determining what radiation dose it would correspond with. Now, if we can quantify the radiation dose which the mineral has perhaps accumulated a signal for in the environment, and we can quantify the radiation dose rate, which comes from measurement of the natural radioactivity of the sample and its environment and its cosmic radiation, we can calculate the time which this dose would have taken to accumulate on the assumptions of our system, if you like. And this creates a dating system which, when it works well, can work with an age range from roughly 0. The youngest luminescence data I ever measured was 0.6 of a year, plus or minus 0.2. and up to approximately 1 million year, which is a very useful timescale for studying human evolution and dispersal, and also the quaternary environmental changes. The uncertainties are very variable, dependent on the luminescence properties of the minerals in question. They tend to be a fraction of the age, and a typical target would be to aim for precision and accuracy between 5 and 10% of age. So for samples of 1,000 years old, we would hope to be able to resolve 50 to 100 year time intervals. For 100,000 years, we are looking at several thousand year uncertainties. We have many interesting ways of stimulating luminescence. They include automated equipment that can do the heating and the irradiation, the calibration. They include steerable lasers, which can be pointed down small recesses, even to stimulate single mineral grains. We are interested in my lab in trying to look at the relationship with an electron microscope between the single grains and their luminescence properties, which is an interesting field. What about the dose rates? Well, the sources of contribution to how fast the clock is running are the natural primordial nuclides, potassium-40, and a little bit of contribution from rubidium-87, the uranium and thorium decay series, and their products. So we have beta and gamma radiation, and from the natural decay series, alpha, beta, and gamma. And we also have cosmic radiation from the deposition environment. The short range alpha and beta radiation comes from within the dating sample, and the gamma and cosmic come from within the environment. How do we measure the dose rates? Well, in my lab, we try where possible to use a portable gamma ray spectrometer to measure the environmental dose rate contribution, which is typically 20 to 30% of the total dose rate in the field, but that's not always possible. So we sometimes bring samples back. We measure the beta dose rates directly from dry samples in the lab, and we use high-resolution gamma ray spectrometry to produce, let's say, an analysis of the composition of the natural sources. Occasionally, we measure the concentrations of the parents using inductively coupled plasma spectrometry, or in the past, neutron activation analysis, and also very occasionally, where we suspect disequilibrium in the uranium decay series, we may use alpha spectrometry or mass spectrometry. And of course, these are just measurement of what's in the sample. In order to calculate the dose rates, we need to model the microdosimetry. Now, I want to show you some examples of the many that we have been involved in over the years, starting with archaeological deposits in the Northern Isles, north of Scotland, the islands of Orkney. I've been running projects for a very long time, looking at different materials, starting in the 1980s with heated materials, which are heated stones. The fireplace of a prehistoric house, the last time it is heated in these islands is the last time the house was occupied. And if that resets the thermoluminescence signal, we can gain an impression directly of when people left their houses. We also have been doing work on wind-blown sands, on sediments accumulated within archaeological stratigraphies, which are themselves, in some cases, signs of extreme storm events. And they have impact on human occupation. They're sometimes related to abandonment of settlements, and they're also linked partly to the Atlantic climate system. This is an old study at the site of Toft's Ness, which is a prehistoric settlement mound in the island of Sandy in the Orkney archipelago. This is very old thermoluminescence dating data, but there are two Neolithic structures, one of which has a heated material mean age of 2,600 BC, another one, 2,250, and they're in the right stratigraphic order. After this, there's a sterile period on the site where a clean wind-blown sand accumulates across agricultural systems. And that sand has been dated by a later PhD student, Anne Somerville, who now lives in Canada. It's in her paper in the Holocene. She finds that the sand was deposited approximately 2,100 BC. at a period when Greenland ice cores show a marked increase in sodium ion concentration, which is interpreted as a sign of a stormy Atlantic period with seawater being captured by the Greenland ice. This is a prehistoric stone circle in the mainland of Orkney called the Ring of Brodgar, one of the famous stone circles of the British Isles. It had a rock-cut ditch, 105 meters in diameter, whose fill was excavated by archaeologists. And this is a set of luminescence data which shows two things. One is that the sediments accumulated very rapidly between about 2,500 BC and about 2000 BC, and then there was a natural sequence of slow accumulation afterwards. And when we took quartz out of these sediments and measured its response to radiation, we discovered an interesting thing, which is that most of the quartz from the stony sediment, which is locally derived, had very little luminescence, 100 photon counts per gray of radiation. And the gray of radiation is probably what you might get in 500 years of age. Not very much. But there is a thin layer in both of the ditches excavated, which has quartz, which has 500 times more luminescence. It's quartz that has a completely different defect structure and geological origin. And this quartz comes in also about 2000 BC at a time which corresponds with this period of storminess. And it also corresponds to a period in the stratigraphy where we think the major Neolithic society of these islands, which is a World Heritage Site, was coming to the end of its period. So this is an interesting environmental event registered in the stratigraphy, dated by luminescence, but also somehow linked into a societal change. And another example, this from the island of Shetland, from the north of Unst. On the beach, there is a Viking longhouse, which was excavated by Jerry Bigelow, an American archaeologist, in the 1970s. And Jerry and I went back to excavate the backfield of this site in 2013, because he knew that there were windblown sands in between the cultural material layers, which he thought represented an environmental stress on this marginal settlement. We measured the luminescence from profiling samples, I'll say a bit more about that later on, above and within the cultural layers. And to cut a long story short, we found that the post-abandonment sand came from the 18th century AD, but the sands that were coming in towards the end of the occupation came from approximately 1200 AD, which is one of those periods in the climate record I showed you where the medieval warm period was beginning to be followed by the first cold period. If I collect data from all of the sandstorms that we've dated in my lab and some of the published literature, I can find periods of which the two I'm just referring to here, there's a slight inflection here, around about 800 years ago, and another period here corresponding to the Little Ice Age, where we get evidence of a lot of sand movement and erosional events. There's another period here, about 2,500 years ago, which is in the archaeological record in the Middle Iron Age. And there's my Neolithic event here, where we're beginning to see inflections in the frequency of these storm recorded sands. This is tentative picture, which is building slowly, but we're beginning to see regional patterns of increased storminess, which seem to fit into certain periods. Esperanza's mentioned the famous portable OSL reader. We realized in working in Southeast Asia that even with some of the world's most able sedimentologists, it wasn't always easy to predict which part of a sedimentary sequence had an interruption or a reversal or a redeposition of material that might have been light exposed but put in the wrong place. And I developed a series of instruments which allowed us to take the equipment to the field rather than the samples to the lab. We see here a second generation one of our instruments, There is Ed Rhodes, who used to be in UCLA, And here's the famous Esperanza Munoz Salinas walking out of SUERC with a smile on her face and one of our portable readers, which is sitting down your corridor. This is the first one that I made in 2005, just ahead of a field trip to Thailand to look at the tsunami sediments following the December 2004 tsunami. We wanted to look at sediments in the field to see whether or not there were residual luminescent signals as part of a study of whether we felt it was possible to date paleotsunamis. I think this intermediate version is probably what you have, isn't it? And we now have this rather nice one-box units. So I'm going to skip this one because I'm conscious that time is marching on, but there's a paper which published this in 2010, which included a case study of a prehistoric landscape in the south of Italy, where wheat cultivation was produced for the first time approximately 6000 BC. And the enclosures have a humid soil at the base covered with a very arid soil, which in fact turns out to be part of the regional substrate redeposited. There has been speculation that wheat cultivation came to the south of Italy by colonization across the Adriatic Ocean, Sea, and that this particular complex, which made 700 enclosures, seems to have started and stopped within 1,000 years. And there has been speculation that it was a change of aridity and climate that stopped the cultivation of wheat in this part of Italy. There are many studies now. The paper has been cited 75 times, and I think we have made these instruments for 25 research groups. And people are using them for different things, but here is an early study of Esperanzas looking at Australian rivers, where the sedimentary sequences show a discontinuity. You can see it in the visual between what was called the swampy meadow sediment and what was called post-settlement alluvium. And in one strand of Australian geomorphology, it is suggested that European farming is responsible for a change in catchment landscape use, which leads to catastrophic soil erosion. Now, the luminescence profiles that Esperanza and Paul Bishop recorded, here are examples in their 2011 paper, which show a marked discontinuity in the luminescence signal around this boundary. I'm not going to interpret this for you since the author is sitting in front of me, but that discontinuity is a combination of the removal of material which has been redeposited without full zeroing, and also the transposition of sediments coming from a different part of the catchment during extreme floods, I suppose. And my last example, and then I will try to make some conclusions, concerns projects in the Red Sea. It's that older one, which has been part of a 15-year study from Professor Jeff Bailey, currently in York University, who's been interested in the routes for human dispersal out of Africa and how they couple to the glacial cycles. There are lots of questions about why early hominin leave Africa and whether they are or are not related to environmental change. There's a model which Oxford University have proposed called the Saharan lung model, which supposes that cyclic humidity and aridity in the Sahara provides opportunities for people to move north, but then, let's say, a vector which forces them to leave. Jeff is interested in the southern migration route towards India, and whether or not it comes across this way and encounters the Zagros Mountains through the interior of Saudi, which is today arid, or might have involved a southern crossing of the Red Sea or a coastal migration route. And he has conducted a series of searches both in the littoral fringe today, but also in the underwater paleolandscapes, which would have been the terrestrial landscape in the height of the Ice Age, where the sea level was 100 meters lower. So a cruise was organized by the Hellenic Marine Research Center in 2013 to look at the Faroe Islands in the southern area of the Red Sea, just north of the Yemeni border, with a series of 18 cores collected from the inner and outer shells. Here are the islands. And we have done luminescence profiling, I think, on 5 of them. and I'm going to show you the profiles for several of these on the outer shelf and the inner shelf. By taking the equipment to the Marine Research Centre and protecting these cores from light until they're opened and analysed, we're able to get dense signals looking at the expression of signal accumulation versus depth. These are scales in meters. And from the outer shelf, we find very smooth, reproducible profiles, not very high intensities. Only in a few cases, about 3 meters under the present seafloor, do we start seeing a climb towards higher signal levels. And when we go to the inner shelf, on the other hand, we have cores, we have 2 of them so far, where we come in and then we have an abrupt discontinuity with a much larger signal at the bottom. And I think with the limited time, I'd perhaps tell you that having taken samples from these back to the laboratory and analysed them, we've been able to show that this small signal, which we see on inner and outer shells for the top 2 meters, is actually quite late Holocene sediment, but the sediment at the bottom comes from the late Pleistocene. And if we position it on the sea level curves for the Red Sea, we're able to position these samples in an environment where today they're sitting under 100 meters of sea level, but at the height of the last glacial maximum, they will have been on the terrestrial fringe. So this has, for the first time in 15 years, found the first evidence for the environmental niches which have been sought in these archaeological exploration projects. So there is another example of luminescence dating, taking us into a past environment and positioning it spatially and temporally. And I think I have to bring things to a close because I'm sure that my time is up and my welcome will be lost if I speak for too much longer. But just to summarize the OSL chronologies for this project, we have worked in the terrestrial side as well. And on what is currently the arid Arabian Peninsula, we have got examples of sediments which are indurated and cemented, which implies they've been through at least 2 cycles of humidity and aridity, going back to 200 to 300,000 years. So we must not assume that that which is arid today was always arid. In the dispersed project, I've shown you the evidence here that we have finally found where to look in the nearshore environment for the Pleistocene sediments, which would have been from the period in glacial maxima, which might have the archaeological landscapes for early human migration on them. In some of the terrestrial sites, we've got components in marine oxygen isotope stage 5, the one that I said was slightly warmer than today and slightly higher sea level. And we are indeed of the view that relationships between sea level positions and paleoenvironmental conditions are critical to future research, and that the luminescence techniques do have a role to play. So now let me try and sum up the big picture message with reference to the big unanswerable questions that I outlined at the beginning. First of all, the small question, can stimulated luminescence method reveal rapid environmental change on decadal, centennial, and millennial scales? Well, just in the small examples I've shown you, the answer is also clearly yes. We've been able to show where we find evidence of enhanced storminess in the Neolithic, and it does correspond in the sites I've shown you to periods of human abandonment of landscapes. We've also found the periods in the Little Ice Age period and the Iron Age which show similar behavior. And in the Pleistocene marine terrestrial transitions, we can spot the process relics, which logic says should be there, associated with sea level change driven by the glacial climate cycles. So if I try to make a general conclusion, clearly both radiometrics and luminescence can register changes in environmental conditions, which is so important to linking past experience to future environmental changes. The harder question is, can the lessons of the past help to guide and inform our responses to the future? And I can only answer that as an optimist by saying, I hope so. Thank you.
Please. Doctor, I would like to know if cesium, this isotope, is more sensitive to radiometrics when you measure all this radiation in the United Kingdom. Is there another isotope more sensitive for radiometrics?
Today, if we look in the UK, we won't see very much cesium. The sources of cesium in the UK were global weapons testing fallout, which deposits only maybe 2,000 or 4,000 becquerels per square meter. We had local sources from our nuclear reprocessing plant, which locally concentrates to maybe hundreds of kilobecquerels per square meter, and the Chernobyl input was up to about 30,000 becquerels. When we look to the natural sources of radionuclides in the environment, each square meter cut to a depth of 30 centimeters has 300,000 becquerels of potassium-40. And that, of course, can be used as a tracer of environmental processes because it's, let's say, it's an indicator of soil type, if you like. And we also can see the radionuclides from the uranium and thorium decay series, Business-214 and Thallium-208 especially, but a little bit of Actinium-228 as well. So those are also available for tracing environmental systems. Does that answer your question?
Yes, of course.
Thank you.
Thank you. And the migration of this cesium isotope, well, the social problem, what was the demands, I don't know, against the Chernobyl authorities or
Yes.
the country?
I think with Chernobyl, I don't know whether you actually know something about this, but my understanding is that amongst the problems are whether people lose their trust in authority when the environment is contaminated after a nuclear accident. It's very difficult for people who are exposed to the consequence to retain their belief in the safety and security of their environment. And I'm sure this was true in Ukraine as well. I have met Ukrainian ecologists in Japan, actually, who said that the most successful technique that Ukrainian and Soviet, in fact, authorities had to help regain trust was to give the radiation detectors to people to monitor their own environments. And that is also true in Japan. Fukushima is a big prefecture with 2 million people. It's north of Tokyo, and yet the nuclear power station was called the Tokyo Electric Power Company, and it was producing electricity for consumption outside the prefecture. The prefecture is was a very valuable agricultural environment. They made 30-40% of the best fruits and vegetables in Japan, and people lost confidence in the market. So the rural economy suffered enormously. There was cattle farming, the great Wagyu beef, and contamination of rice feed led to contaminated food, which probably wasn't radiologically dangerous, but it was very harmful to people's sense of well-being to think that the environment that they had such a high connection and pride in was somehow spoiled. So I think the greatest cost in these cases isn't just the radiological consequence, it's also what people's sense of well-being when they realize they have to live in it. And I suppose the last thing which you're almost hinting at is, if the radioactivity is moving, is that something, let's say, that people want to know about, or they want to, as it were, forget about it? I like to believe that knowledge helps make people feel more comfortable in their environment. And certainly anecdotally, that's what we found in Japan, that when we're making measurements on the ground with people, they were interested in what they could see and actually made it easier for them to think they understood how to navigate space through the environment. Does that give you something?
Thank you.
Thank you.
¿Alguna otra pregunta?
Yes.
In your experience in this luminescence methods application on environment change, in the case of Sonora is the north of Mexico,
Yes.
This arid place. What is the potentiality of this study to apply in this?
Well, this is part of what I hope we will find out in the rest of the week. But I don't know enough about the environmental history of Sonora, and I hope perhaps that colleagues here do, but has it always been arid? Has it been, if it has always been arid, has the remobilization of sediments in an arid environment been a constant process, a seasonal process, a process that has episodes of movement and episodes of accumulation and stasis? Those, I think, are the kinds of questions. But maybe I can invite Esperanza to comment on, do we know where the framework should start in this area? You've studied the rivers, I think, yeah?
Yeah, of course. But in the north of Mexico, I am starting these studies in this area, so we'll see what.
And I suppose another question to ask people here is: would you say that the north of Mexico is an environment which is particularly vulnerable to environmental change, or is it already is it under special dynamic threats that need to be monitored today? Is it already so hot that it can't get worse?
Paleontologists are in the field to see the change of climate with
through the organisms,
pollens, for example.
Yes.
The evolution of the pollens.
Pollens, exactly. Yes. Does the pollen record suggest that you have different vegetation in the past? Yeah. And humidity?
The Sierra Madre Occidental.
Yes. And greater humidity as well in the past? Was there greater humidity in the past?
It goes along. I mean, if it's hotter, it's drier. If it's cooler, it's wetter.
Yeah, simple as that. Yeah. And therefore,
there's changes in the
yes,
in plants.
Yes.
Vegetation.
Yes. Okay.
Yeah.
One of the things interesting about the case of Sonora is that we are pretty close to the United States, where they have carried on the bomb testing and nuclear testing. So there are no studies about the case of cesium here in Sonora. We are pretty close, so that would be a very interesting area to explore.
Interesting, yes.
And also to explore soil erosion and those sort of things. Yeah, absolutely.
Yes. Okay. Well, it would be very interesting to see what you managed to do in this.
There is a nuclear plant in Arizona, very close.
Okay, so let's monitor the cesium.
West from Phoenix.
Yeah. If the nuclear plant is working properly, there should be no cesium coming out of it. Okay. Let's hope that is the case. Good.
So I don't know if there are some questions from. So maybe we can go ahead with the talk outside with some coffee.
Well, thank you very much.
Thank you.
Okay.